Hi, welcome to Module 2, Session 3 of the course Data Science for Engineers by the Department of AA and DS. Now let us go to the sixth data visualization technique, that is data normalization. So what is the problem for the given graph? So can you find out some drawbacks of this given graph where the x-axis contains some sales value, total bill value, and y-axis contains the corresponding count of those bill values. So it's not difficult to see that some of the values are too much hyped up and some are very low. So when you have a data in both ends of the spectrum, when we have data which is very high and very low, then we have to rescale that. So that is what we will be learning right now, and this process is called data normalization. Now, to begin with, try to answer this question, like how can you normalize the data, let's say, which is contained in an array that ranges from A to B. Okay, so if there is a set of data that is ranging from A to B, can you normalize that values between 0 and 1? So we are trying to rescale the values from A to B in between 0 and 1. Like for example, if you have some data between 15 and 25, so how can you put those data or rescale those data in between 0 and 1? Okay, so let's see how you do that. So in the new set of data, in the normalized set of data, a data that resides between A and B would be converted to this new x bar, which is equal to the corresponding data. So for example, if the data is between 15 and 25, that is A and B is 15 and 25, and assume that we are talking about a value 18. So 18 would be converted in between 0 and 1 by using this formula, where x is 18 and min of x is the minimum value in the range. So that is A is the minimum value and maximum is B. So 15 to 25, so we have the data 18, so that would be converted to 18 minus min of the array, which is 15. So 18 minus 15 divided by max of x minus min of x, so that is B minus A. B is the maximum value because it ranges from A to B. The domain of the previous values is from A to B. Now if you use this formula, then we can get the corresponding place of 18, the value 18 in between 0 and 1. So this is very simple rescaling. So x minus A divided by B minus A. Okay, so this is for rescaling between 0 and 1. Now let us try to generalize this. So you are given a vector x containing numerical or fractional values which is ranging from x min to x max. So like previously we had A to B. So here the minimum value of the vector is x min and the maximum is x max. So this is the domain. Now normalize this vector x in between ranges of A and B. So before it was 0 and 1, but right now we are making it more general in between A and B, where surely A is less than B. Let's see how we can do that. So the normalized data would be equal to A plus x minus x min divided by x max minus x min into B minus A. So let us study this one by one. Like what is the meaning of x minus x min divided by x max minus x min? So this is in fact the previous formula, right? So by x minus x min divided by x max minus x min, we have just normalized these values in between 0 and 1. So x min to x max, all these values that belongs to this domain could be made or rescaled or normalized in between 0 and 1 by using x minus x min divided by x max minus x min. Now when you multiply by using B minus A, suppose that the data was from 15 to 25, that is x min is 15 and x max is 25, and we are trying to normalize that in between a and b. So assume that a and b is 30 to 40, right? So in that case, b minus a would be 40 minus 30. So the data that was between 0 and 1, we have rescaled that between 0 and 10, that is 40 and 30, that is b minus a is 40 minus 30, and plus a, that is plus 30. So once we have made it in between the gap of a and b, that is in this example, that is 30 to 40, so gap is 10. Now we have to rescale that to 30 to 40, right? So for that, just add 30, the minimum value of a and b. So that's why it becomes x normalized is equal to a plus x minus x min divided by x max minus x min into b minus a, where x is the value that resides in between x min and x max. So this is the final thing. So this is the most generic formula for normalizing any numbers that is between a and b to c and d. Okay, the generic form of data normalization. So it is not over yet. So if you have a data vector like this, you can see here values 3, 4, then 9,999, and then you have 10 and 1. So it's very easy to see that that 4 nines, 9,999, is kind of overshadowing all the other values. So if you just simply plot this in the XY graph, you would be getting a very big value for a a big column. If you're going for a column chart, you'll be getting value for the 4 9, but 3 4 10 1, it won't be in a visualizable format. So you cannot even see whether 3 4 10 and 1 is there in the data. Now if we use if you try to convert this in between 0 and 1, then 3 would be converted to point 003 or something like that, a very small value, and 9999 will be converted to, let's say, something like 1 or point 0.999. So whatever value, even then, if you convert that by using the previous generic equation, even then this will not work. So we are going to apply a logarithmic function in order to convert this in such a way that we can plot this all the values 3 4 and 10 1 and 4 9s. We have to see all these values, not like the graph here that we are seeing right now. So for that, we can use log normalization, and this is the equation for the log normalization, that is log of x plus 1. So if you apply log of x plus 1, and after that, if you plot this data, then you can see some value for each of this, value 1, value 2, all 4 nines. We can see that. What happens is, because it's logarithmic, so you can think what happens. What is log of something like 10,000 to the base of 10? Log of 10,000 to the base of 10. That value is equal to 4. So it became a smaller value, right? And if you throw log of 3 to the base of 10, you will be getting a value less than 1. But then the gap is less, right? Something less than 1 and value 4, not like in the previous case. So this is how we are using the power of exponentiation, or the power of logarithm, in order to visualize the data. So in such cases, when you have one value overshadowing all the other values, if you want to plot it in a practical way, then we can use log x plus 1. So why we have plus 1 there? It's not log x, right? We have log x plus 1 because if you have value 1, that value is not 0. So when we rescale by using log normalization, if you are not putting log of x plus 1, it would be log of x, which is log of 1, that is equal to 0. But 1 should not be scaled to 0 because 0 is nothing. But 1 has some value in it, right? So that's why we are putting log of x plus 1. So if the value is 1, then, or if the value is non-zero, then we will be getting a log of 1 point, like whichever value is there, and any value that is greater than 1, the log of a value that is greater than 1 is non-zero. Okay, so this is the reason why we are putting log of x plus 1, in order to avoid cases where when x is 1, it should not become 0. It should not be converted to 0. Okay, it should be having some value when we normalize that. Okay, excuse me. So let's go to the new data visualization technique called box plots. It's also called box and whisker plots. So box plot, it typically displays a 5 number summary of the data. These are the 5 number summary: the minimum, the first quartile, the median, the third quartile, and the maximum value. Why we use box plots? We are using box plots to find out the anomalies or outliers in the data. So I've given a template for that. Here you can see so how we are constructing a box plot. So first of all, we'll find out the first quartile, third quartile, and the value from the first to the third quartile would be normal values. Any value that goes to the left of Q1, that is first quartile, and any value that goes to the right of Q3, which is the third quartile, would be considered as outliers. So we will see this very clearly by using examples and algorithm, that how we are constructing a box plot. So let us start with an example. Assume that this is the data that you have: 25, 28, 29, 29, 30, 34, 35, 35, 37, 38. So let's see how we can plot a box plot. So first of all, whenever you get this kind of numerical data, always arrange this data in the sorted order, which is the ascending order, that is the smallest to the greatest, and then find out the median value of that new list, and then find out the two quartiles. And the first quartile is the median of the data points to the left of the median that you found out in step 2, and the third quartile is the median of the data points to the right of the median that you found out in step 2. Now this will give you the 5 number summary. If you have the min and max, which is very trivial, right? The min and max values of this list. So then you have all the summary that you need, and you can categorize the anomalies as anomalies. So let us see how we can do. For this example, first of all, data 25 to 38. What is the median value? The median value here is 32. How it is 32? Because let's count how many values are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 values are here. So what we will do, we can take the middle value, or we can take the fifth and the sixth values and find the average. So here what we have done is we took the fifth value, that is 30, and the sixth value, that is 34, and we average that to find out the median. Okay, so 30 plus 34 divided by 2. So why we went for that, taking two middle values and finding out the average? Because if you are having odd number, then we can easily find out the median, right? If we have 3 numbers, let's say 5, 10, and 13, so we know that 10 is the middle, because to the left of 10 there is one number, and to the right of 10 there is one number. So if it is odd number, just simply take the middle value. If it is an even number, then you divide by 2. So whatever value you get, you take that value and the value after that and find out the average. So that's why, since we have 10 values, we took the fifth value and the sixth value, that is 30 and 34, and we found out the average of that. 30 plus 34 divided by 2, which is 64 by 2, 32. So that is the median. So we got the median. So just focus on the template that is there, the bar number line template at the bottom that you can see. There is the minimum value, the maximum value, Q1, Q3, and median. So right now we have found out the median value, that is 32. Now what is the max and min value here? So since it is arranged in ascending order, the max value is 38 and the min value is 25. So we have got 3 values out of the 5 number summary. Now we have to find out Q1 and Q3. That is the first quartile and the third quartile. So what is Q1? It is the median of the data points to the left of the median. So what is median? Median is 32, right? So to the left of the median, how many values we have? We have 25, 28, 29, 29, and 30. So we have 5 values. So just divide 5 by 2. Okay, so divide by 5 by 2. So we will get 2.5. Okay, so make it into the higher just the higher integer value, that is 3. So when you have 5 values, just exactly take the middle value, and since we have 5 is the value here, 5 by 2, 2.5, so we can take the third value. So out of 25, 28, 29, 29, 30, the third value is 29. So that is Q1. As you can see in the right side, Q1 is quarter 1 value. Similarly, for finding out the third quartile, we have to go to the right of the median, that is right of 32, which is again 5 values, that is 34, 35, 35, 37, 38. So again we have to take the third value here, which is 35. Okay, 35, that is the third value, like 5 by 2, 2.5, CL of 2.5, 3. So we have to take 35. So Q1 is 29 and Q3 is 35. Now, if you ask me what are the anomalies, all the numbers that is less than 29 and all the numbers that is greater than 35, that is all the numbers that is less than Q1 and all the numbers that is greater than Q3, they can be considered as anomalies or outliers in the data. So here if you think what is to the left of 29, yeah, we have 25 and 28, that could be considered as anomalies, and to the right of 35 we have 37 and 38, that could be considered as anomalies. Okay, so this is one method, right? So let us see the most concrete method. So generally to find out anomalies, people don't just take to the left of Q1 and left of Q2. There are more appropriate methods for that, and it is just one extension to box plot. Let's see that. So finding anomalies using box plot. So this is the actual way in which we can find anomalies. That is, prepare the box plot with all the 5 summary values and then find out Q3 minus Q1. So Q3 minus Q1 is known as IQR, or interquartile range. Interquartile range, IQR. So find out IQR, Q3 minus Q1, and then any point that lies less than Q1 minus 1.5 times IQR can be considered as an anomaly, and any point that is greater than Q3 plus 1.5 times into IQR is also considered as anomaly. So to the left and right, this is the actual equation that we can use to find out the anomaly. And don't take to the left of Q1 and left of Q3. That gives some anomalous, some statistics it gives you, but that is not the classical or widely accepted way to find out anomalies by using box plots. So this is the way, that is, take Q1 minus 1.5 times IQR, whatever lies to the left of that, they are anomalies, and whatever lies to the right of Q3 plus 1.5 times IQR is also considered as anomalies. So let us see this by an example. So this is the data. It's already arranged in ascending order, which makes our life easy. Okay, so we have 10, 12, 13, it goes on like that till 30, 32 and 100. And find out all the anomalies in the data. That is a question. Okay, so first of all, find out Q1, right? So for finding out Q1 and Q3, I'm not going to repeat the same steps again. So like we did in the previous example, you find out the middle or the median value of the data, of the sorted data, and for finding out Q1, you find out the median of the left part of the data that goes to the left of the median. Find out the median of that. So if you follow the steps, you will see that Q1 is 15 and the median of the right part of the actual median, that is Q3, would be 29. Okay, so you can use the same method that we checked on the previous example. Okay, to the left of median, which is the median, that is 15, and to the right of the median, what is the median, that is Q3, which is 29, and IQR is Q3 minus Q1, that is 29 minus 15, which is equal to 14. Okay, now how to find out the lower bound that we saw, that is the left lower bound, that is IQR, right? I mean Q1 minus IQR into 1.5 times, right? So Q1, which is 15, minus IQR, that is 14 into 1.5 times. Okay, find out that value. So that would be 21, right? IQR into 1.5 is IQR into 1.5 is 21, and the lower bound is Q1 minus IQR into 1.5, that is 15 minus 21, that is minus 6. And the upper bound, that is the right part, what is the bound that we have? That is Q3 plus 1.5 times IQR, that is Q3 is 29, so 29 plus 21, which is 50. So any value that goes below minus 6 or above 50 is considered as anomaly. So here in the given data, do we have any value that is less than minus 6? No. So there is no anomaly in the left hand side. So what about the right hand side? Do we have any values that is greater than 50? Yes, we have, which is 100. So 100 is the outlier. Or in fact, we can tell that 100 is the only outlier in the given data. Okay, so this is how we find out anomalies by using box plots. Thank you.